Okay, let's dive in. If you follow environmental policy, you know sustainable fisheries management is, well, critical. We often assume the science is basically settled. Count the fish, understand the biology, set the quotas. Simple, right? But what if the very foundations of that science,
Okay.
the building blocks,
Hmm.
are still kind of shaky, even after decades?
That's pretty much the core message we get from this deep dive into a 2015 paper.
Yeah,
It's called Contemporary Fisheries Stock Assessment. Many issues still remain, by Mark Maunder and Kevin Piner.
moderate and minor, right?
Yeah. And their goal wasn't really to, tear everything down. They aimed to be honest brokers, using the data itself. They wanted to really highlight how much research is still needed to properly improve stock assessments, to make sure our management is grounded in reality, not just statistical best guesses.
And the historical angle is fascinating. They point out it's been over half a century since Beverton and Holt's big 1957 manual.
Mm.
And yet, Maunder and Piner are saying we're still grappling with the exact same fundamental issues. Fish growth, natural mortality, recruitment, selectivity, how the gear actually works. It feels a bit like we've been stuck on the same problems for 50 years.
It is surprising, especially because the tools have changed so much. We're way beyond the older methods like VPA, which needed perfect age data. Now, assessments use these really complex integrated models, things like stock synthesis, CSL.
Integrated models. They sound pretty heavy-duty. Why the shift to something so complex?
Well, mainly because real-world data is almost always incomplete or messy. Integrated models let you throw everything you have, surveys, catch data, age or link samples, into one big statistical framework. They're essential when you don't have, say, a perfect unbroken time series of age data, which is, frankly, most of the time. They try to piece together the whole picture from all the fragments.
Okay, piecing fragments together sounds good, but only if the underlying picture you're aiming for is right. And this seems to be where the real challenge lies, estimating absolute abundance.
Exactly. That's the number you actually need to set a total allowable catch, the TAC.
Right.
But here's the catch, pardon the pun. In these big, complex models, many of the crucial biological processes, things like the growth rate or how many fish die naturally, are often just fixed, set at predetermined values based on old studies or assumptions.
Hold on. Fixed. You mean they aren't actually estimated from the data you're putting into the model itself?
Often, no. Not directly. They're treated as known inputs. And because the models are so complex, the way the actual data interacts with these fixed assumptions can lead to some unexpected or unstable results for the population size. The paper's central point is really stark. Your estimate of absolute abundance fundamentally depends on getting those assumptions about the population, the fishing process, and the sampling right. If they're off, your final number is likely off too.
Let's dig into the data types they talk about. First up, relative abundance indices, like catch per unit effort, CPUE, or data from surveys. These show trends, right? Up or down.
Yeah, they give you the trend, but not the actual number of fish. The big issue there is catchability.
Catchability.
Yeah.
That's like how effective the fishing gear or the survey net is.
Exactly. It's the conversion factor. It turns your relative index fish caught per hour, say, into the absolute number of fish out there.
So why can't we just measure that efficiency really well once and call it good?
Because it almost certainly doesn't stay constant. It's rarely known precisely to begin with, so it has to be estimated within the model. But worse, it probably varies over time. Think about environmental changes, currents, temperature, oxygen levels. These can change how fish cluster, meaning your standard survey tow might catch way more or way fewer fish, even if the total population size hasn't changed at all.
Okay, so that variability introduces a lot of noise, a lot of uncertainty.
A huge amount. And it's really hard to track or account for perfectly, even in well-designed surveys.
So if these indices aren't a direct count, how do models use them to estimate the total biomass?
Primarily through depletion. The idea is if you know how much fish you've caught the total removals, and you see the index go down by a certain amount, you can sort of back calculate what the original population size must have been.
Okay, makes sense conceptually.
It gets complicated immediately by those production processes we mentioned. New fish are being recruited, existing fish are growing, and others are dying naturally. All at the same time, you're fishing. So you're not just measuring depletion against a static pool, you're trying to hit a moving target.
Right. Which brings us to the other key data, composition data. Age and length measurements. Age data is considered the gold standard historically. How does knowing the ages help estimate the total number?
It's indirect, mostly through estimating fishing mortality, which we call F. Basically, the age structure tells you how hard the population is being fished. If F is high, you simply won't see many old fish surviving. They get caught before they get old. And since we usually have decent data on the total catch, and we know that F is roughly catch divided by the total biomass, B, if we can estimate F from the age structure, we can work backwards to estimate B, the absolute abundance.
That's clever. Like looking at the proportion of old trees in a forest to figure out how heavily it's being logged, if you know the total timber harvested.
Exactly. It's a similar logic.
Yeah.
But what happens when you can't reliably age the fish? This is super common, especially for tropical species or fish without clear growth rings. You use length data instead.
And that's where things get even trickier, according to the paper.
Oh, yeah. Because using length data effectively requires really precise knowledge of not just the average length at age, but also the variation around that average. How much do lengths differ for fish of the same age? Maunder and Piner show that the model estimates for F and total biomass can be incredibly sensitive to small changes in your assumptions about the length or the variability in length for the oldest fish in the population.
Wow. So if you assume the biggest fish reach, say, 1 meter at age 10, but in reality they only reached 90 centimeters or there's more variation, that small discrepancy could massively throw off your estimate of the total stock size.
It absolutely can. You're essentially forcing the model to interpret the length data through a biological lens, the growth pattern that might be fundamentally wrong, and that error propagates through the whole assessment.
Okay, this really sets the stage for the 4 big uncertainties. They highlight the ones that have apparently dogged fisheries science for 50 years. Let's tackle growth first. We tend to think we got a decent handle on growth, right?
You'd think so, but the paper argues it's often poorly estimated, particularly for species that grow fast and live short lives, like many tropical fish. They give examples like dolphin fish, where growth estimates are all over the place depending on whether you use otoliths, ear bones, scales, or just length data. Even for well-studied fish like Pacific cod, sometimes the model suggests the standard otolith aging might be systematically biased, maybe adding an extra false ring.
And the critical missing piece you mentioned earlier is the variation in length at age.
Exactly. Most growth studies focus only on the average length. They don't report or maybe even estimate the variation properly, but the stock assessment models need that variation input. So analysts often have to just assume a value for it, and that assumption can have a surprisingly large impact on the final management advice.
Okay, uncertainty number 2, natural mortality, or M. This feels like the big one. It dictates how productive the stock is, how much you can sustainably harvest.
It's absolutely fundamental, and for most fish stocks, we have shockingly little reliable direct information about M. It's like the ghost in the machine. Most assessments have to rely on these indirect methods, correlating M with how long fish live or their growth rate, using formulas derived across many different species. But the paper cites a major review which found basically none of these common indirect methods are precise enough for modern assessments.
And we usually treat M as just a single constant number over time in the models, don't we?
We do, largely for stability. But reality is almost certainly more complex. M likely varies with age, maybe sex, definitely density, probably the environment, just like growth does. By fixing it, we introduce a potentially major structural error right at the heart of the model.
Yikes. Okay, uncertainty 3, recruitment. The number of new young fish entering the population each year and how it relates to the size of the parent stock.
Yeah, the stock recruitment relationship, it's notoriously difficult to pin down. There's usually huge environmental noise. One year conditions are great for survival, the next they're terrible, regardless of how many parents there were. Plus, you often lack contrast in the data. Maybe the spawning stock has always been relatively high, so you don't have data points showing what happens when it gets really low.
And the paper points out a specific statistical bias here.
Yes, a really concerning one. Simulation studies consistently show that when you try to estimate the steepness of this relationship, how quickly recruitment drops off as the parent stock declines, you often get a positive bias.
Meaning, the model tends to lean towards recruitment being independent of stock size. It thinks the stock is more resilient than it might be.
Precisely. It makes the stock look overly optimistic, like it can keep pumping out recruits even when the spawning biomass is quite low. This bias can directly lead to setting catch limits that are too high and potentially unsustainable. And trying to solve this with meta-analysis, borrowing parameters from other stocks, doesn't really fix it because those other stock assessments are likely suffering from the same underlying bias.
Right, the bias gets baked in everywhere. Okay, final key, uncertainty. Selectivity. Which fish are actually caught by the fishing gear? Seems like we should know this. We designed the nets.
You'd think. But the mathematical functions used in models to describe selectivity are often too simple, too inflexible. They might assume, for example, that once a fish reaches a certain size, its chance of being caught stays high indefinitely in asymptotic curve. But real-world factors, like how fishing effort is distributed spatially or how fish behavior changes with age, can create more complex patterns. Specifically, the paper highlights the problem of dome-shaped selectivity.
Dome-shaped,
Yeah.
meaning the very largest, oldest fish actually become less likely to be caught than medium-sized adults.
Exactly. Maybe they move offshore or learn to avoid the gear. This is a big problem because it can create cryptic biomass. If the oldest, often most fecund fish are effectively hiding from the fishery, the model doesn't see them properly. It looks at the catch, sees mostly medium fish, and might overestimate the fishing mortality needed to produce that catch composition, potentially leading to an underestimate of the total stock size and, again, overly optimistic catch advice.
Okay, so we have these deep, persistent uncertainties in growth, mortality, recruitment, and selectivity. Given all this uncertainty, how do scientists actually check if their complex models are producing sensible results? Are there diagnostic tools?
That's a critical point Maunder and Pater make. There's a general lack of standardized, widely used diagnostic tools, but they do highlight a couple of promising ones. One is the R0 likelihood component profile diagnostic.
R0, that's like the unfished population size, the theoretical starting point.
Essentially, yes, it scales a whole population. The diagnostic works by fixing R0 at several different possible values from low to high. For each fixed value, you calculate how well each separate piece of data fits the model. You plot the likelihood score for the survey index, the age data, the length data, etc. against R0.
Ah, I see. So you're asking each data set, what overall population size are you think is most likely given the model structure?
Exactly. And if different data components point to wildly different values of R0, if the survey data suggests a huge population, but the age data suggests a small one, then, you have a major conflict. It's a powerful way to see which data sources are driving the result and if they fundamentally disagree about the scale of the stock. It's been used to diagnose problems like misspecified selectivity.
It sounds really useful.
Yeah.
What about the other one, the age-structured production model, or ASPM, diagnostic?
This one's a bit simpler conceptually. You compare the results from your full, complex, integrated model with results from a much simpler model in ASPM. This basic ASPM ignores all the age and length composition data and just assumes recruitment follows a standard stock recruitment curve.
Why compare against such a simple model?
To isolate the influence of the composition data, you're asking, can the trend in the abundance index be explained reasonably well just by the total catches we know we took out? Or is the complex age length data forcing the model to estimate a population size or trend that's wildly different? If the full model gives a drastically different picture of stock status than the simple ASPM, it flags that the composition data, or perhaps the assumptions about how it relates to the biology, like growth or selectivity, might be inappropriately driving the overall result. It helps pinpoint where the potential problems lie.
Okay, moving toward the bigger picture. If these fundamental issues, growth, recruitment, selectivity, have been known for so long, why haven't we solved them? The paper suggests it's not just scientific difficulty, but systemic issues.
Absolutely. They pull no punches here. First, there's the issue of funding and data quality. Even for valuable fisheries, the resources dedicated to collecting the essential data needed for robust assessment are often insufficient. Or sometimes funds get diverted to, say, long-term ecosystem research, which, while valuable, doesn't address the immediate critical uncertainties plaguing the stock assessments needed now. There's an opportunity cost.
And beyond money, they point to a bottleneck in expertise.
Yes, potentially an even bigger obstacle. A global shortage of highly trained stock assessment scientists. These models require serious quantitative skills, applied math, advanced statistics. The existing pool of experts is relatively small and incredibly overburdened. Developing the deep graduate training, maybe even postdoctoral work, focused specifically on assessment methods and theory.
And then there's the distraction factor, the public perception issue.
Right. The paper notes how high-profile scientific journals sometimes publish controversial papers, perhaps focusing on the dire state of fisheries, which might use flawed methods or data. These grab huge media headlines. The consequence is that the already busy assessment scientists have to spend precious time analyzing these papers, writing rebuttals, and trying to correct public misinformation, diverting their limited time and energy away from doing the core research needed to improve assessments in the first place.
So we're facing a confluence of issues, funding gaps, a shortage of specialists, and valuable time being siphoned off. Maunder and Piner wrap up by basically saying fishery science is at a crossroads.
They really do. They frame it as a clear choice between two paths forward. Path one: commit to a massive, coordinated, properly funded research effort to finally resolve these fundamental uncertainties. Really nail down growth estimation, validate aging methods across the board, find reliable ways to estimate M directly, figure out recruitment dynamics and selectivity patterns. It's the deep dive into foundational biology.
That sounds like a huge undertaking. What's option two?
Option two is more pragmatic, perhaps. Acknowledge that fully resolving these deep uncertainties might take decades or might even be impossible for some stocks. So instead, focus research effort on designing management strategies that are robust to this uncertainty. These approaches, often called management strategy evaluation or MSE, use simulations to test different harvesting rules under a wide range of plausible biological scenarios, including our uncertainties about M or recruitment. The goal is to find rules that perform reasonably well, meet conservation and yield objectives across that whole range of uncertainty, even if we don't know the precise true state of nature.
So it's a choice between trying to find the true biological answers
Yeah,
versus designing management systems that work well enough despite not knowing all the answers.
that's a good way to put it. Do we invest everything in foundational science, hoping for breakthroughs, or do we focus on building resilient governance systems that can function effectively in the face of the uncertainties we know exist?
That leaves us with a really profound question to chew on. Where should the balance of effort lie? Chasing those elusive biological truths that have puzzled scientists for over half a century, or engineering clever management procedures that accept our ignorance and aim for robustness? It's a critical decision for the future of managing our oceans.
It certainly is a tough choice with major implications.
Thank you for joining us for this deep dive into the state of fisheries assessment science.